The next step we're going to take in looking at our systems of so we've done lots of mathematical background up to now, and we have a little bit more before we start thinking about concepts, what's happening in the solutions. We're going to be thinking about equilibrium. Right, we've looked at phase equilibria, so what's the equilibrium between two phases of just a single substance, and now we're looking at equilibrium in something with multiple components. Now, if we're thinking about a mixture, what we can say is that the Gibbs energy at equilibrium, well, we know overall that the overall G for the system is going to be the Gibbs energy for the solution, so I'll write that as Ln, so that's our mixture of our two liquids, plus the Gibbs energy of the vapor, right? And again, we're ignoring solids. We're assuming our system isn't cold enough to freeze. The other thing we know is that when the Gibbs free energy doesn't change, there's no net change of entropy, and there's no driving force. This is the condition for equilibrium, right? Is that we have no net change of Gibbs free energy. Okay. Now, what we're going to do here is that we have to keep track of the number of moles of stuff in different phases, right? We're going to have the number of moles of component 1, that's in solution. We'll have the number of moles of component 1 in the vapor. And we need to think about how does G change as all these changes. So this is all going to be related to chemical potentials, right? How does G change as we change the number of moles in different phases and in different phases. We're not considering any reactions here, so 1 isn't going to turn into 2 or anything like that. That'll be later. We will get to reactions and thinking about equilibria and reactions. We have the number of moles of component 2 in solution and number of moles of component 2 in the vapor phase. So we're going to keep track of all of these. To make this very general, we can just say any of these is an NJ, right? We have 4 different N's we have to keep track of, but we can keep track of them by calling them J. Now, if we're going to be having a change in the number of moles in any of these phases, right, that's going to be some dNJ, right? There's some change in the number of moles. And we're going to fix temperature and pressure, right? We have constant temperature and pressure. That's sort of the natural thing to do with the Gibbs energy. That's what helps us. That's what tells us whether things are spontaneous or not. So we can say that dG overall for the system is whatever dG is for the solution plus whatever dG is for the vapor. Right, so this is just the differential form of this equation that we wrote up here. And then we can go ahead and say that, okay, well, these dG values are going to be, right, how does G of the solution change with the number of moles of component J in the solution, keeping temperature, pressure, etc. Constant times the change in the number of moles of J in solution plus dG vapor dN J vapor, keeping temperature, pressure, etc. constant times dNJ vapor. Right, so this should look familiar. We've seen something like this when we were talking about single component systems, right? Here we have chemical potential of component J in solution times dNJ solution plus chemical potential of component J in the vapor times dNJ vapor. Hopefully you're seeing a trend here, right? That this is something we've seen before. But one thing we do know is that if we're thinking about one specific component, Nj, right, this is either component 1 or component 2, that any change in the moles of J in the solution has to be matched by a change in the moles of J in the vapor, right? These are equal to each other. And so that gets us to this equation, mu J vapor minus mu J solution times the change in the moles of J in the vapor. We've seen an equation just like this when we were talking about a single component system instead of a multi-component system. This is a completely analogous equation. So the same criteria apply, that whatever has the lowest chemical potential, the substance will transfer to that phase, right? So at equilibrium, where there's no net change in the number of moles, we know that these two have to be equal to each other. and otherwise the system will move towards the lowest chemical potential. So whether that's the vapor or the solution, this is the same thing we saw with phases. Now this is useful because we can, if we're thinking about equilibrium, it's much easier to write out the chemical potential for a gas phase substance than it is for a solution. And so this gives us a way to easily express at equilibrium what the chemical potential of the entire system looks like for both the vapor and the solution. Right? We know that at equilibrium, this expression holds, right? That the vapor and the solution have the same chemical potential. So if we can write out the chemical potential for one of these, we can also write it out for the other one. It's the same. So we can take advantage of this fact and look at the chemical potential of the vapor, right? So mu J and the solution is equal to mu J for the gas phase, the vapor phase. And we can write out the chemical potential for the vapor phase is going to be mu J naught, so the standard value of the chemical potential, plus RT log Pj over Pj naught. Okay, where did this come from? This is an analogy. This is analogous to the equation G bar equals G bar naught as a function of temperature at a specific temperature times RT log P over P naught. This is an equation that we derived. This is from equation 22.59. This is an equation we derived for an ideal gas. And that is the assumption here is that the vapor behaves according to ideal gas behavior. This is how does G change as a function of pressure. So this is an integral we solved a couple chapters ago. And just as a reminder, what does the naught mean? Pj naught means 1 bar. That's our definition of our standard state. Okay, so that's pretty straightforward. We assume ideal gas behavior. We can write it out this way. And we can then take another step to get rid of, we'd ideally not like to have this expression here, right? We'd rather not have this standard state here. So let's look at the, for a pure substance, we can write that mu J star for a liquid is the same as mu J star for the gas, right? So the star, again, this is, if we're thinking now, going back to phase diagrams in a single component, we can write out a very similar expression that we have mu J naught at that given temperature plus RT log Pj star over Pj naught. All right, and so the point of doing this is that we now have a way of getting rid of some of our extra terms here. Right, and so we can write out for the solution, we can write out for the single component by itself, and now we can take equation 1 up here and subtract equation 2 down here, and that lets us get rid of the standards, right? So we can say that mu J solution minus mu J star for the liquid, or for the gas, but we'll stick with the liquid, is equal to mu J naught minus mu J naught. So those two terms will cancel out. And then we'll have the second term plus RT log Pj minus RT log Pj star. And the P naughts have canceled out as well. I didn't explicitly write those out, but we'll have a minus P naught term for each of those, and both of those will cancel each other out. And so that also lets us get rid of the standard pressure as part of all this. What we get at the end is that the chemical potential for our solution, which is the same as it is for the vapor phase, which is why this all works, is equal to the chemical potential for the pure substance, at liquid or gas at this given temperature and pressure, plus RT log, and combining these two log terms here, Pj over Pj star. Okay, and that's what we were trying to get to all along. That's what all this was about, was getting this equation here. So the chemical potential for our component 1 or 2 in our solution is equal to the chemical potential of the pure substance, which is a constant, which is what's nice, and this term that's in terms of the vapor pressure. So Pj here, this is the vapor pressure in the solution. So what's the difference between these? This is the vapor pressure when the things mix together, whereas this Pj with the star on the bottom, this is the pure substance vapor pressure. So what we need to understand is how does the vapor pressure change as we have different compositions of things? Right? If we can understand how the behavior of Pj, the vapor pressure of the solution for that component changes with composition, then we can understand the chemical potential and what's going to be the behavior of the system. And that's sort of what the rest of this chapter is dedicated to, is to understanding what's happening there and different types of solutions that we can consider.